Alright, let's dive into one of the most mind-bending topics in modern science, negative-parameter metamaterials. Imagine a material that, when you push it, doesn't just push back, but actually helps you push it further. Or a material that expands when you squeeze it. Sounds impossible, right? But that's the wild world of negative-parameter metamaterials. So, what does negative parameter even mean? Normally, materials have positive properties like mass density or stiffness. But with clever engineering, especially around certain resonance frequencies, scientists have found ways to flip these properties, literally make them negative. Take negative mass density, for example. This means that if you try to accelerate the material, it actually moves out of phase with the force. Think of a rubber ball that jumps away from your hand before you even throw it. Or a negative bulk modulus, where stretching the material makes it want to compress, a bit like a spring that pulls inward when you try to yank it apart. If you combine both negative mass density and negative modulus, you get a mechanical analog of negative index materials, just like the wild stuff we see in optics. But how do you make this happen? One way is by designing structures at the microscopic level, like tiny metal spheres coated with rubber, arranged in a crystal lattice. These units resonate at certain frequencies, much lower than the typical wave interactions you'd expect. Depending on how you tune these resonances, you can actually get the mass density or stiffness to go negative. Now, let's talk compressibility. Negative compressibility means a material expands when you squeeze it. In crystals like methanol monohydrate, or even in clever honeycomb lattices, you see these bizarre effects in 1, 2, or even 3 dimensions. Sometimes it's about geometry, sometimes mixing materials, or setting specific constraints. The results? Materials that could protect deep-sea sensors, mimic muscles, or power the next generation of microdevices. And don't forget negative stiffness. Most things resist deformation, but negative stiffness materials actually welcome it. They deform more and more as you push. They're so unstable on their own, so we combine them with stable materials for uses like seismic protection, vibration control, or even cloaking objects from sound waves. All this science fiction is becoming science fact, and the applications are only getting crazier. Metamaterials with negative parameters are changing the way we think about what's possible in physics and engineering. Imagine what's next.